So, in previous class we went through this example. So, I drew this edge dislocation which had some step, and you were to find out whether it is a kink or a jog, and next you had to find out whether the different sections U1, U2, U3, U4, U5 what are their directions, and also that they are screw and edge. So, in this particular example we used edge dislocation. Next we will try to do the same thing with a screw dislocation. So, here the screw dislocation is given to you. Here this is the screw dislocation, and this is coming out of plane, this step, then there is a section parallel to this, then again coming back and here, and this is a whole screw dislocation, and it is given that this is 1 1 1 plane, and the Berger vector for this is given as a by 2 1 1 0. So, first thing is to find out whether it is a kink or a jog. Now, the way it is drawn, it has been given that this is the slip plane, this 1 1 1 is the slip plane for the screw dislocation, and you have to describe the characteristics of the various sections U1, U2, U3, U4, U5. So, let us start and see. I hope you have given a try it on your own. If you have, then it will you will find it, you will be able to compare your notes with mine. If not, then you can go through the solution here. So, here what we have, Berger vector is given as a by 2, implies line direction for this is also equal to 1 bar 1 0. So, the line vector for this U1 and U5 is bar 1 0, and U3 we said it is since U2 the way it has been drawn, and I have explained that U3 is parallel. So is U3, U3 is also equal to 1 1 0, and for all of them Berger vector is also equal to a by 2 1 bar 1 0, they are parallel. So, all U1, U3, U5 are screw dislocation. For the U2 and U4, what you see is that the Berger vector is going like this. So, here it is also like this, here it is also like this. So, for these sections it was parallel, but U2 and U4 you see it is going perpendicular. Moreover, U2 is coming out of the plane, just normal to the plane, but normal to the plane is given as 1 1 1. It means that U2 equal to U4 is equal to, direction should be same as the normal, which is 1 1 1, and here the Berger vector is equal to a by 2 1 bar 1 0, and these are perpendicular as you can see, hence this must be a screw the edge dislocation. Next we want to find whether this step is kink or jog. That is the simplest part. We said that kink will be in the plane of the slip, while jog takes it out of the slip plane, and here it clearly coming out of the slip plane. Therefore, this step formation step is a jog. So, that solves this problem. So, now let us summarize some of the important aspects that we have learned so far, and in the process we will also list out how these kinks and jogs are generated, what are the usual mechanism. So, what are the some of the things that we have learnt today or based on the jogs and kinks? That movement of dislocation generates jogs and even kinks. In fact, this will become more clear when we come to the last point, as you will see in a moment. And another thing that you would realize is that when a step is formed, sometimes they have the similar characters, sometimes they have different characters. So, these steps severely influence motion of dislocation. So, these two are kind of interrelated. Steps are severely influencing the motion of dislocation, and dislocation motion is creating these steps, and this is what you can describe as non-linear plastic deformation. So, there is not one to one relation, it is there are other ways that it is getting influenced, getting dampened and so on. So, this is the typical description of a non-linear plastic deformation, and that is why you cannot explain every effect in a very simple something like a Hooke's law that we use in elastic elongation. Now, we have talked about generation of jogs and kinks, which is by movement of dislocation. So, now if we are talking about generation of jogs and kinks, you should know that there are 3 distinct mechanisms which lead to generation of these jogs and kinks. What are these? So, there are 3 mechanisms. Jogs it is thermally generated, meaning because the jog is trying to the climb is trying to take place, and because of that there will be thermally activated jog formation. So, there can be thermal activation of jogs, and similarly there can be thermal activation of kinks. Similarly, there can be thermal activation of kinks. So, these two are actually part and parcel of the same thing. So, you can imagine something like a straight dislocation, and because of thermal agitation there may be steps like this when it was gliding like this, and therefore, this will keep moving. So, this will move like this, which in effect will lead to this direction motion of the overall dislocation. Similarly, you can have extra half plane and there may be jogs formed. These jogs would move in the opposite directions, leading to an effective movement of the dislocation half plane. So, this will lead to climb up. Now, the third mechanism for generation of jogs and kinks, which is very important with respect to plastic deformation, is intersection of dislocations. So, when you start deforming, what happens that certain dislocations will get generated, and you keep applying the stress, dislocations move, and when more and more dislocations are present, then these dislocations will interact, and when they interact they will lead to formation of some steps, kinks and jogs. And when these kinks and jogs are formed, some of them will be glacial, which is they will be movable, some of them will be sessile, meaning they will be non-movable, and because of that this leads to what is called as the plastic hardening or the work hardening of the material, because there are more and more dislocations, they interact, they intersect, they form forest, what is called as forest dislocations, because there are some immobile dislocations. So, the overall strength of the material increases, as we showed you in one of the earlier lectures describing about dislocation, that there is 2 regime of dislocation, one almost 0 dislocation where the strength is again very high, and then a very high dislocation density where again your strength can increase to certain extent. So, in this particular case our intersection of dislocation leads to improvement or increase in the strength, because of some of them will be glacial and sessile. Okay, so, let us try to understand intersection of dislocation in a bit more descriptive way. So, here we will now start the intersection of dislocation. So, our topic here is dislocation intersection, and here so far you would realize that we are focusing only on very simple description of dislocation, and here we will continue that. We have not yet talked about specific kind of dislocations inside a specific system, for example, a edge dislocation or a screw dislocation in a FCC. Very rarely once in a while we do touch upon the topic, but we have not described the structure in so much detail. so far we assume that one single plane can describe the extra half plane for a edge dislocation, which is not really true for either FCC or a BCC, both of which were one of the simplest systems. So, coming back to this, we will continue our utilization of this simple description. So, in other words, what we are saying is that we are assuming a simple cube type of system where the slip direction is 1 0 0 and the slip plane is also of 1 0 0. That is what it means when we mean that, when we say. So, for this particular kind of system, you will get the dislocation description the way we have described it. Okay, so, here we will describe 4 cases. So, first we will take 2 edge dislocation. So, this is one edge dislocation and the other one we have here is like this. So, in this particular case, the Berger vector for the 2 of them are like this. So, if this is this one, let us call it dislocation 1. So, we will call it B1E. So, Berger vector is going down, as you see, this is one horizontal plane, this is one vertical plane. So, this Berger vector is going down, as you would realize, because this is a edge dislocation and this is coming in this parallel to this edge, and this we will describe as B2E. And let us assume that the dislocation is this particular dislocation is moving in this direction. So, what will be the final shape of this? Let us see. Actually, I need to so, this particular dislocation that we had, so it is moving down and down, and then at certain point it will intersect with this, and when it intersects, this leads to a step formation here, and this is how this step formation takes place, like this and like this. We will come back and describe more about the step, but for now just understand that this is the step formation in this. So, it was on one plane, it has a part of it has now moved to another slip plane. And what happens to this one? This one actually makes just a small difference which will not be really observable, and which is that it moves one step to the left. Okay. We will come back and describe all these in more detail, or not basically we will describe what is happening once we have looked at all the 4 cases. So, this was our B2E, this was our B1E. Now, let us go to case 2. Here also we have 2 edge dislocations, but they are oriented differently. Here in this particular case you can see the 2 Berger vectors are perpendicular to each other, but we can have same Berger vector, but the dislocation line can be oriented perpendicular to each other, and this is how it will be. So, this is one plane, this is another plane, this is same dislocation B1E. So, it is Berger vector is like this, but now in this particular plane, so imagine like this one has been, this particular plane that you see has been rotated by 90 degrees along this axis, and so the same dislocation can be assumed to be here, but now since it has been rotated by 90 degrees, so the Berger vector here is B2E. Now, B1E and B2E are parallel, as you can see here. So, this is a different case from here. So, do not get confused that both of them are edge dislocation. So, they are same. No, it is not. This one is Berger vectors are perpendicular, here they are parallel. And here also B1E is moving down. So, this one is moving on this plane and keeps moving on, at certain point it will intersect this dislocation line whose Berger vector is B2E. So, what happens? So, let us see that. So, this dislocation line has come down, and what has happened to it we will describe. So, first let me draw a dotted line to show which is the line of intersection, and on this particular line of intersection we had the dislocation like this, and this dislocation has gotten a step along this line. So, this is what happens to B1E, and what happens to B2E, which is over here. This also gets a step along this line. So, this is the line which is the common line for these two planes, and both of them have gotten a step along this line which is common to this. So, they have received a step, they have obtained a step, and as you can see in these two cases clearly that there are step getting formed because of intersection of dislocations. So, these are two cases. Now, let us move on to the case 3. Now, here we will have one screw dislocation involved. We will not be able to show the plane for the screw dislocation for the slip plane, but we will show the plane for the edge dislocation. So, let us say the screw dislocation is like this. So, this is the plane, and on this particular plane we will have the edge dislocation. So, the edge dislocation is like this, and we will say it is B1E, while this is the screw dislocation whose Berger vector. So, this Berger vector is like this, and for this the Berger vector is like this B. So, this is a screw dislocation. So, we will call it B2S. So, as you can imagine, because of this screw dislocation there is this ledge getting formed, which in effect also describes its slip plane. Okay. So, now this will become the slip plane. Now, this is a arbitrarily defined slip plane right now, it could have been any other direction. So, whatever we describe next with respect to kink and jog would be assuming that this is the slip plane. If it were different, we may get different result, but that will not be the case for other cases that we are describing, where we are only talking about edge dislocation. Their slip plane will get defined by the motion in the direction in which it is moving, and the final result will also not change as long as you assume that constraints that the Berger vectors are perpendicular in the first case and parallel in the second case. Okay. So, coming back to this, so we will describe that this particular edge dislocation is moving like this. So, what is the final scenario? In this particular case, what we get is so the edge dislocation comes over here and it gets a step. And now it is in a different plane, which is in the lower ledge. So, that's so this edge dislocation has again received a step, and so will the screw dislocation, which was over here. It will receive as it will also receive a step, and this will be so this is the step over here, and here we had B1E, and remember the Berger vector does not change. These are some of the fundamental rules that you must remember when you are trying to solve problems related to dislocation. So, the Berger vector here is still B1e and it will remain same for the steps or the whole dislocation. Here also the Berger vector will remain the same way that is for the edge dislocation or the screw dislocation. So, that is the case 3, and here also we see steps getting formed by the movement of dislocation. Now, let us look at case 4. Case 4 is when we have two screw dislocations intersecting. So, like I said that it is not possible or to describe easily the plane. So, you would see I will just draw the screw dislocation line, and here the other one is almost perpendicular to it, not almost, but it is in a perpendicular plane, and so we will say this is B1s and this is B2s. These are, so you have to imagine that these two are perpendicular. So, let us write it down somewhere here. And over here we will assume that this dislocation is moving, or you can imagine that this one is moving along this direction. So, what is the final step that you will get or final configuration that you will get? You will get this dislocation will also get a step. So, here again we have steps getting formed over here. Now, do you see a pattern to what is how these steps are getting formed? The pattern here is, so let us go back and look, this is moving and it forms a step in this direction. What is this direction? It is same as the direction for the Berger vector. Where is the step forming? It is moving in this direction, it is which is parallel to the Berger vector in this direction. When you have something like this, in both of this the Berger vector is the same direction, and therefore, the step you see is also getting formed in the same direction. What happens here? So, the Berger vector screw dislocation is like this, and therefore, it leads to the step in the edge dislocation in this direction. The Berger vector for the edge dislocation is like this, which will mean that the screw dislocation will get a step in that direction. So, here you have a step in the screw dislocation like this. In case 4, here the two screw dislocations are intersecting and both of them have Berger vector perpendicular to each other, and the line vector, the step vector that you get, they will have the step direction or the step line vector would be. So, this line vector would be parallel to this Berger vector, this step will be parallel to this Berger vector. So, in simple words we can say that when two dislocations intersect, each, okay, it will happen to both because there is nothing special about one, each acquires a step equal in direction and length. Okay, so, this is another aspect, length of the step is also equal to Berger vector of the other. Okay, so, first thing each acquires. So, do not get confused that why this one was not getting a step. This is also getting a step, but only that you will not be able to see, it is in the direction of the line vector of this particular dislocation. Second is that the step, let us say this is we signified with S, then the length of S is equal to length of the Berger vector. So, this is step in 1 is equal to Berger vector length of the Berger vector of 2, and the direction of S is also equal to the Berger vector B2. S1. So, length of S1 is equal to B2, length of and direction of S1 is equal to B2. So, coming back here, if you look at this particular length or this step is equal to, so I do not want to draw too many lines here because we have other things to show over here. So, this step that we are looking at, for this, so let us say this is step S, the magnitude of this S is equal to the magnitude of B1, because this is S2, this is happening in dislocation 2. So, I will call it S2, magnitude of S2 is equal to magnitude of the Berger vector B1, and this direction is equal to Berger vector 1. So, it is pointing in that same direction, or S1 I should say, is parallel to B1. So, with this I will just describe it at one place. It should become clear that what are the important aspects of dislocation intersection. So, these are the different cases, and we will get to see a few more things about this dislocation intersection. And the most important part we have already understood is that when two dislocations intersect, each acquire a step. And not only that, but the step has certain characteristics, it is not just in arbitrary direction. In each of these, for example, even here if you look both of them. So, if you talk about, so let us for the sake of completion, because here we had only one clear step visible. So, for the sake of completion, let me do it here for this one. S2 is equal to B1 and S2 is parallel to B1, and for this one, which is step 1, magnitude of this is equal to B2 and S1 is parallel to B2. Now, based on this, we will come back and look at whether it is kink or a edge, and whether it is kink or a jog, and whether it is in the same plane or it is in the other plane, it is whether it has a screw character or a edge character. So, to just one more step, one more point here, that since we have described that this has one unit length, so we can say that we know that energy per unit length of a dislocation is equal to alpha GB square. So, for if you look at the step, we can say energy is equal to alpha GB square into length is what, is equal to B. So, it will become alpha GB cube. So, each step, and here we are not talking about the per unit length, because we already know the length, which is very small and it does not have very long range of effect. So, alpha GB cube, where alpha is of the order of 0.2. So, this is additional information that we can get here about the step. So, we will come back to this point and we will discuss more on the whether kink or jog character and edge and screw character. So, see you in the next class.